In this problem, let's consider the exponential Diophantine equation 4 to the power of a minus 36 to the power of b equal to 28, and we seek all integer pairs a, b that satisfy it. First, let me establish the domain. We can suppose that a is less than 0. Then, if a is less than 0, then we will know that 4 to the power of a is a positive rational number strictly less than 1. Because this will be the reciprocal of a number that is greater than 1. And then the equation can be rewritten as 4 to the power of a equals to 28 plus 36 to the power of b. And since the right-hand side is an integer, this will force 4 to the power of a to be an integer, which is impossible for a is less than 0. So we have reached a contradiction. And then the same contradiction will rise if you let b is less than 0. So, thus we'll have here a contradiction. This allows us to conclude that both exponents must be non-negative integers. So, we have a and b both are greater than or equal to 0. Now, I will use modular arithmetic to constrain the shape of a. We can reduce the equation modulo 7. Now, we know that 36 is congruent to 1 mod 7, which just means that when 36 is divided by 7, the remainder is going to be 1. And we know that by the property of congruence modulo, 36 to the power of b is congruent to 1 to the power of b, which is just 1 mod 7 for all integers b. So then the original equation will imply that 4 to the power of a minus 1 is congruent to 28 congruent to 0 mod 7. So we'll have 4 to the power of a congruent to 1 mod 7. And no smaller positive exponent yields 1 than 4 cubed. Hence, you'll have a must be congruent to 0 mod 3. This will narrow the candidates down to a equals to a multiple of 3, so 3, 6, 9, 8. But more structures needed to handle b. To find out how to get b, we have to analyze the powers of 2. We can rewrite both terms in terms of base 2. So we have 4 to the power of a equals to 2 squared to the power of a, which is 2 to the power of 2a. And 36 to the power of b equals to 2 to the power of 2b, because 36 is 4 times 9, times 2 to the power of 3 to the power of 2b, which is 9 to the power of b. So then we can factor the left-hand side. So we'll have 4 to the power of a minus 36 to the power of b is equal to, after factoring out the 2 to the power of 2b, 2 squared a minus b minus 3 to the power of 2b. So then, we'll get that the equation will become, this portion we know equals to 28, which is 2 squared times 7. And then we can consider the p-adic valuation v2, which counts the exponent of 2 dividing an integer. On the left, we have an explicit factor 2 to the power of 2b. The bracket 2 to the power of 2 times a minus b, and then minus 3 to the power of 2b is an integer. And it may be odd or even, but in any case, v2 of the product is at least 2b. So in simple words, on the right, we have v2 times 28 equals to 2. Therefore, v2 times 2 to the power of 2b is less than or equal to v2 times 28. So we'll have 2b is less than or equal to 2. b is less than or equal to 1. And this is the key bound. There are only two possible values to check, b equals to 0 and b equals to 1. So let's check the case where b equals to 0. Then the equation becomes 4 to the power of a minus 36 to the power of 0, which is 1, which is 4 to the power of a minus 1 equals to 28. 4 to the power of a equals to 29. And we know that 4 to the power of a takes powers of 4, not 29. Hence, no solution. Second case, b equals to 1 would give us 4 to the power of a minus 36 to the power of 1 equals to 28. 4 to the power of a would equal to 64. A equals to 3. Hence, the solution would then become AB will equal to 3, 1. And that is going to be the only solution to this problem.